So here we're given a function h of x, and we want to, it's already written in standard form because our numerator and denominator are both in standard form. We want to convert it to factored form and then simplified form. And we want to do that in order to find our x-intercept, y-intercept, holes, vertical, and both of our asymptotes. Under each one of our key features for a rational function, we have a how-to. So how to find that particular key feature given either or any of the forms. So you want to make sure that you read the how-to. And I'm going to do this one as an example. And this always works. So first we want to factor our numerator and denominator of our rational function in order to get it into factored form. So I'm going to set up my parentheses for our binomial factors. And since our leading coefficient is just 1, I know that I'm going to have an x as the first term in both of my binomials. And then I need to figure out in our numerator what two factors of 56, or what two numbers multiply together to give us 56, but add together to give us -1. So I know that one of the factors of 56 are 7 and 8. And in order to get 7 and 8 to equal -1, that would have to be -8 plus 7 would give us -1. So this would be the factored form of our numerator. In the factored form of our denominator, again, I'm looking for what two numbers multiply together to give me 42, but add together to give us +1. So I know that two factors of 42 are 6 and 7. So I know that that would have to be -6 plus 7 would give us +1. So this would be our factored form. And our simplified form would just be, once we simplify, creating our giant 1, right? Our new factored form would just be x minus 8 over x minus 6, because we were able to cancel out that factor of x plus 7 using our multiplicative identity property. So now we have all three forms, and we're going to look to see what our how-to says to find each of these different key features. So for x-intercept, it says, from simplified form, set the numerator equal to 0 and solve, right? So x-intercepts happen when y, or f of x, or h of x in this case, is equal to 0. Because we're dealing with rational functions, which means ratios, which means fractions, since our functions are always in the form of a fraction, and fractions can only be equal to 0 when the numerator is 0, in order to find our x-intercept and make our whole function equal to 0, we just have to set the numerator of our ratio equal to 0. So let's go ahead and do that. I'm going to take my numerator in simplified form and set it equal to 0, just like it says, and solve. So we have an x-intercept at 8. Okay, so now let's look at what it says for y-intercept. Well, it says from any form, evaluate when x is equal to 0. Well, I'm going to evaluate in simplified form again just because it has the fewest number of x's. I'm going to set all my x's equal to 0 just like it says, and I'm going to solve. Excuse me. Okay, so that 4 over 3 is the same as 1/3, so we have a y-intercept at 1/3. All right, now let's find our holes. Well, we know that our holes happen for any restricted value that we were able to draw a 1 through. And that's kind of what it says here in more complicated terms. I always think of like hole in 1 or a hole at 1, right? So the restricted value where we drew the hole would have been -7. -7 would have made our denominator 0, but we were able to cancel it out or draw our giant 1 through it. But instead of making a vertical asymptote, it's going to make a hole. So at -7, we would have a hole because that's a restricted value. And the other restricted value would give us our vertical asymptote. So we had our other restricted value at 6. Right? So we had two restricted values, 6 and -7. -7 created a hole because we had to draw 1 through it. +6 created a vertical asymptote. So those are numbers that our function will never exist at. They just have two different reactions, right? And you can read what it says for how to find the vertical asymptote. For horizontal asymptote, it says in standard form, approximate the end behavior using the leading terms. So you're just looking at these two terms in standard form, and you're writing them as a fraction, and that is 1, right? So you can kind of think about the horizontal asymptote is like as from standard form, as x is getting bigger and bigger and bigger, your numerator and denominator are getting just as big, just as fast. It really doesn't matter if you have like infinity squared minus 56 is still infinity, right? And infinity squared minus 42 is still infinity. So these other terms in these trinomials kind of cancel them. They don't really matter as x gets extremely big. So you can just kind of focus on what's getting biggest the fastest and focus on those and then ask yourself what is happening. If this x squared wasn't here and it was just x over x squared, then you would know that your horizontal asymptote would be at 0 because your numerator is getting bigger faster. I'm sorry, your denominator is getting bigger faster than your numerator. And you've done some examples like that. So now let's look at how we graph this. So I like to start with my asymptotes. So I have a vertical asymptote at 6. So I'm going to just draw my vertical asymptote here at x equals 6. We had a horizontal asymptote at 1, positive 1. Y equals 1. And then I'm going to plot my intercepts. So I have an x-intercept at 8 on my x-axis. And I have a y-intercept at 1.3 approximately. So about 1.3, right? A little less than 1.5. So I always plot my holes last because it kind of just involves erasing and drawing a hole in my graph. So I'm going to have a hole at -7. So I'm going to draw my graph. So I know that my graph is going to exist. I kind of think of this in 4 different quadrants, right? Since we divided this into 4 pieces, like you have this quadrant, this quadrant, this quadrant, and this quadrant. So I'm looking at where does my graph exist. I know it's going to exist in 2 of those because I have a vertical and a horizontal asymptote that's dividing this. So I know that my graph is going to exist here in this quadrant because our y-intercept exists there, right? So it has to. And I know that it's going to exist here because our x-intercept exists here. So I'm going to carefully draw my graph, right? Approaching our vertical and horizontal asymptotes, but never touching. And do the same thing here and going through our x and our y axis. Intercept, sorry. And then at -7, I'm going to erase. And I'm going to draw an open circle to represent my hole. And there you have it, people. Okay. I'm going to do one example from Delta Math to the best of my ability. So this example right here. All right, so I know that I'm going to have, so first of all, I can't factor my numerator. I can't factor my denominator. This is already in simplest form. I know that my function cannot exist when x is equal to 3.5, right? Because 2 times 3.5 would give me 7. And 7 minus 7 will give me 0. So when x is equal to 3.5, my function can't exist. So that'll be a vertical asymptote. We'll have a vertical asymptote at 3.5, right? Because that would make my denominator 0. But again, nothing is canceling out or turning into a 1, so there's no holes. I will have a horizontal asymptote. Change colors. We'll have a horizontal asymptote. Again, just looking at our leading terms, right? At x over 2x, we can imagine that invisible 1 there, right? Our x's would kind of cancel out. So we will have a horizontal asymptote at 1/2. We have x-intercepts when y is equal to 0, right? So we have an x-intercept when y, so when our numerator is equal to 0, so that'll be -3. And we have a y-intercept when x is equal to 0. So if I set all my x's equal to 0, this will give me 3 over -7. I'll put that in my calculator. 3 divided by 7. So that'll give me approximately -0.42 or 0.43. All right, so now I have, and there's no hole, right? No hole because nothing turned into a 1. So there's no hole in our graph. So now we have all of our different features. And so I'm going to plot this on Delta Math, right? So we have a vertical asymptote at 3.5. So I'm going to click on vertical asymptote and drag it to 3.5 approximately. We said we had a horizontal asymptote at 1/2. Drag that to 1/2 approximately. An x-intercept at -3. A y-intercept at approximately -4.3. So about right there, a little less than -1/2. Okay, we don't have to be perfect. There we go. Whatever. And then no hole. All right, so let's plot our rational function, cross our fingers, submit our answer, and boom. Okay. And some of these are going to turn out to be just straight lines, right? Some of these do simplify to just be in the form y equals mx plus b. And some of them will have asymptotes where they can't exist. Some of them, if they don't have asymptotes, then they're just going to be lines, right? Lines don't have any boundaries like asymptotes cause. All right, so hopefully that was helpful.